Hello there, Mr. Sutton here, bringing you the AB Calculus 6-8 Extra Practice number 3 solutions on motion free response practice. For this calculator-based free response problem, for time greater than or equal to 0, we have this R of t function that represents the speed in kilometers per hour at which a car travels on a straight road, and the number of liters of gas used by the car, x kilometers, to travel x kilometers, is modeled by this g of x function. Okay, so this is kind of interesting. We have this function here that is a function of distance traveled, and we also have this other speed function that's a function of time. Involves distance because we're talking about speed, which is the rate of change of distance, but it doesn't give us distance directly. First task on this already very weird problem is we want to know how many kilometers the car travels during the first 2 hours. Well, if you want to know distance traveled, that's essentially the integral of speed over a certain interval. At least it's the integral of speed if your car is just going in the same direction, which it seems to be based off of what they've given us here. So we're just going to take the antiderivative, we're just going to take the integral of r of t on the interval from 0 to 2. And let's just use the calculator for that. So really the very first thing I'm going to do on my calculator is enter this r of t function as y1. And then let me just quit out of there. And I'm going to do math 9, integral from 0 to 2. Let me do alpha trace y1, put a dx in there, press enter, and that comes out to 206.370, and that's in kilometers. So I'm going to also actually store that in my calculator and on paper as distance A, because just looking ahead, and if you just looked at this problem without looking at anything else, you wouldn't do this. But looking ahead, I know I'm going to need this value later on. So I'm going to store it now as A. So just remember as we do the rest of this problem, this is value A. And let me go on my calculator and store that as well. Alpha A. And that'll help us later on. All right, let's keep going. For this part of the problem, they want us to find the rate of change with respect to time of the number of liters of gas used by the car when time equals 2. Indicate units of measure. All right, so we're talking about this. So the number of liters used by the car for x kilometers is this g of x function. So that's a good starting point. So to find out dg over dt, the amount of gas used with respect to time, we need to take the derivative of this g function. So that would be dg over dx. The trouble is, if we're talking about time, this function by itself doesn't really have time involved. We have x here, which is kind of an inner implicit function of time. So after I take the derivative of this thing, this is kind of an outer function. Once you take the derivative of that, you have to use the chain rule and multiply by the derivative of x itself with respect to time, so dx over dt. So this is the general setup, and if you just look at the way these fractions are arranged here, if you cancel out these dx's, you would end up with dg over dt. So that's kind of the algebraic end of these derivative chain rule situations. So now let's see what happens when time equals 2. At time equals 2, to take the derivative of g of x at time 2, I basically need to do g prime of, well, how many kilometers had we gone at time 2? We figured that out in part A. We called that constant A. It was like 200 and some change. So I'm going to do g prime of A, which we got in part A, ironically. And now dx over dt, this is going to be the speed, actually, at time 2. And here we have a function for speed of our car, or whatever this vehicle is. Yep, it's a car. So this dx over dt at time 2 is just going to be r of 2. So these are both things we can do on the calculator. Let's do those now. So one thing I'm going to have to do in order to do all this on the calculator, since I want g prime, I need to put g in here. So in y2, I'm putting my g function. I've already got r entered in y1, so quitting out of there now. I needed to do g prime of a. That's what was going on there. Since I've already got the g function defined, I'm just going to go ahead and take the derivative of that on my calculator. I don't actually have to show you what the derivative of g looks like if I'm just taking the derivative at a specific point. So I'm going to do math 8. We'll have a dx down there. I'm taking the derivative of, let's see, alpha trace y2, because that's where I stored the g function. And I'm evaluating that for x equals, now we have that a value that we found in part A, so alpha a. So that gives me g prime of a. Now I have to multiply that, so times r of 2. So that's just going to be alpha trace y1, and I'm plugging just 2 into that. And all of that comes out to 6. So 6 what? Well, here's where we have to get the units. Now, gas is measured in liters. Time is measured in hours. So this is going to be 6 liters per hour. For this last part of the problem, we want to know how many liters of gas have been used by the car when it reaches a speed of 80 kilometers per hour. So in order to answer the how many liters question, we need to know how far the car has gone. We need an x value to plug into the g function. But for the x value, we need to integrate this speed function at a certain time. And in order to do that, we need to know at what time we're doing the integral. So this all starts with figuring out when we reach a speed of 80 kilometers. Then we're going to use that to get a distance traveled, and then we'll use that to get the liters. So let's start by setting r of t equal to 80, and we're going to do that on the calculator. So I'm here in my y equals on the calculator, and I'm going to go to y3 where I haven't put anything yet. I'm going to put 80 in there, and I'm going to be seeing where y1 and y3 intersect. y1 is where I stored r of t. So if I'm going to do this on a graph, I don't want to be graphing this. This was g of x right here. Let me unselect that. And now I'm just graphing y1 and y3. Now on what interval? Well, I don't really know. Something bigger than 0, right? Let me just do zoom 6. Zoom 6, right? Can't go wrong with zoom 6. And let's see if we can at least see where these intersect. Although actually that's not going to help because I need to get up to 80. So let me actually set my window. Let me go from 0 to 10 for the input. And let me zoom 0 that and see if I can see an intersection at that point. Okay, so we see that these things are crossing right about here. So I'm glad that I can see the intersection. Let me do second trace, intersect. There we go. And where's my spider? It's up there, all the way up there. Let's move back to this intersection spot right about here. Let me press enter 1, 2, 3 times. And we're intersecting at about 0.3314. I'm going to call that B, by the way, just so I can refer to it easily. And on my calculator, let me quit out of there, and let me store that value as alpha B. So I'll be using that again very shortly. All right, so that's the time when our car reaches a speed of 80 kilometers per hour. Now, I need to know how far the car goes between 0 and this time. So I need to figure out basically if I want to do x of b, essentially, I need to figure out the integral from 0 to b of the r of t function, dt. So let me go back to the calculator and do that. So I've got math 9 for my integral. We're going from 0 to alpha b. And again, I'm using the r function, so this is going to be alpha trace y1 dx. And I get this number. So this is how many kilometers I actually go in the time that it takes me to reach a speed of 80 kilometers per hour. This 10.7941 and some change. Now I'm going to store that as another constant c so that I can refer to that easily. Let me go on the calculator and let me store that as alpha c. Great. Press enter. There we go. All right, so this is my distance traveled. Now, all I have to do at this point, now that I know how far I've gone, is plug the kilometers, the x that I just found, the c value here, into the g function itself. So at this point, all I'm doing is g of c, and I will also do that on the calculator. Now remember, I stored the g function as y2, so let me do alpha trace y2, open the parentheses, and I'm just going to plug in alpha c there, close the parentheses, and that comes out to about 0.537, and since this is just asking how many liters, that's 0.537 liters. For this problem, we have a car traveling on a straight track. During the time interval 0 to 60 seconds, the velocity and acceleration are continuous functions, and we have a table showing values of both. Nice. Using appropriate units, we want to explain the meaning of integral 30 to 60 absolute value of v of t in terms of motion, and then we want to approximate that with the trapezoidal sum. So let's do the explanation part first. When you're taking the absolute value of velocity and integrating that, that is going to be the total distance traveled by the car and its distance, so that's going to be in units of feet. And that we also have to mention the time interval, so that's going to be from 30 to 60 seconds. Now we actually have to find, or at least approximate, this integral using a trapezoidal approximation. So this is 30 to 60. They want, let's see, 3 subintervals, but they don't have to be equal subintervals. So we're just using these 3 subintervals here. And we just have to be careful doing this because we're taking the absolute value of each of these areas that we're about to find, each of these trapezoidal areas. So for the first one, we have, and I'm just going to say this is all approximately equal to, because we don't have the exact value. We have the absolute value of, let's see, now this interval from 30 to 35, we're using the v row here. So we have the absolute value of negative 14 minus 10 over 2 times a height of 5. Add to that the absolute value of negative 10 plus 0 over 2 times a height of 15 to go from 35 to 50. And then we've got absolute value of 0 plus 10 over 2 times a height of 10. Now we could leave it like this and stick units of feet on the end and call it a day. But if you wanted to simplify, we could do that too. So let's see here. This is negative 24 over 2, which is negative 12. Times 5 is negative 60, but the absolute value of that is positive 60. And over here, this is going to be negative 5 times 15 is negative 75. Absolute value becomes positive 75. And then finally, over here, we've got 10 over 2, which is 5, times 10 is 50. Absolute value of that is still 50. So we have, let's see here, 135 plus 50 is 185 feet. For this part of the problem, they want us to explain the meaning of the integral from 0 to 30 of a of t dt in terms of the car's motion, and then find the exact value of that. So a is the acceleration function. A is the rate of change of velocity. So if I'm integrating that rate from 0 to 30, I am getting the total change in the car's velocity. And that's going to be in units, since it's velocity units, it's going to be in units of feet per second. And we need the time units, or the time interval in here, so that's from 0 to 30 seconds. So all of that's required for a complete full credit response. Now they want us to find the exact value of this integral. The key here is recognizing that a is really the same as v prime of t. So when I take the antiderivative of a, I'm really just getting v evaluated from 0 to 30, which means we're basically doing v of 30 minus v of 0. Now what is v of 30? That's going to be negative 14. V of 0 is negative 20. So I have negative 14 minus negative 20, or negative 14 plus 20, which comes out to 6. And again, that's in units of feet per second. On this part, they're asking for the interval 0 to 60, must there be a time when the velocity is negative 5? Well, if we're trying to guarantee a certain output for a function, and we have at least some information about the original function, we often use the intermediate value theorem. To use this theorem, we have to establish that the function we're trying to get the output for is continuous. Now, they told us here that velocity is a continuous function. I'm just going to spell that out again. That allows us to use the intermediate value theorem. So we have to figure out the velocity at time 0 and time 60, and then show that -5 lies between those two velocities. So at time 60, I'll go with 60 first. Actually, no, let me do time 0 first. Time 0, we have a velocity of -20. At time 60, we have a velocity of 10. And we know that -5 is between -20 and 10. So now once we've shown this and mentioned that v is continuous, by the IVT we have guaranteed that v of c equals -5 for some c value on the interval from 0 to 60. So in essence, yes, there is a time when the velocity is -5. For this last part of the problem, they're asking if there's a time between 0 and 60 when we're guaranteed that the acceleration, a of t, equals 0. This one's a little bit trickier. If you're thinking about using the intermediate value theorem, which is a good first thought because we do have values for acceleration, it's going to be tricky because we only have positive numbers given in this table. So, I mean, if we were changing from negative to positive, then we would be guaranteed that we were hitting 0 somewhere on there because they did tell us the acceleration was continuous. Unfortunately, we don't have any negative numbers here, not even a 0. So there's no guarantees by the intermediate value theorem. By the same token, we're not guaranteed that we don't have an acceleration of 0 by the IVT. The IVT can't exclude values that we don't appear to be hitting. We can only include them. I mean, for all we know, maybe we're dipping down below 0, somewhere between 0 and 15, and then coming back up. But there is another theorem we can use. Although we don't have the right kind of information for the original function, we do have some information about velocity that we might be able to use. Acceleration is the derivative of velocity. So we might be able to guarantee a certain value for the derivative of velocity, namely acceleration, using the mean value theorem. To use this, we have to establish that the function that we're using the MVT for, which is the velocity in this case, is differentiable and continuous on the interval in question. So we do know that we have a continuous acceleration. That means that the velocity itself is going to be differentiable. And it's going to be, they didn't say that, let's see here, they said during the time interval we have continuous functions, so we're differentiable on the interval that matters here. So that means that we can use the MVT. So in order to use the mean value theorem, we have to find the average rate of change on the interval. Now, just taking a quick look here, not any old average rate of change is going to help us out here. For MVT to work, you need to get an average rate of change that's exactly the same as the derivative value that you're trying to prove exists. So if we do the average rate of change between 0 and 60, well, I don't know what it comes out to off the top of my head, but it's not going to come out to 0. We need the velocity to be exactly the same at the endpoints of whatever interval we're doing AROC on in order to get 0 for the output from that. So just taking a look at velocity values that are exactly the same. We do have matching 20s here. 0 and 25 times, those both give us velocities of -20. And those are the only duplicate values in this row. So if we're going to try to use mean value theorem to show that somewhere between 0 and 60 our acceleration is 0, we are going to have to use the interval from 0 to 25. Why? Because it's the only one that's going to work. So let me do then v of 25 minus v of 0 over 25 minus 0. And that's going to be -20 minus -20 all over 25, which comes out to 0. Since we had differentiability on velocity and the average rate of change of velocity is 0, the mean value theorem proves here that acceleration, which is really just the derivative of velocity, must equal 0 somewhere on the interval from 0 to 25, which that means we also have this happening somewhere on the interval from 0 to 60 because this is just a subinterval of the interval they were asking about. For this no calculator free response problem, we have this particle moving on the x-axis with a position given by x of t here on the interval 0 to 2 pi. The first task is to find the time when the particle is farthest to the left. So since this function is essentially measuring how far to the right you are, farthest to the left means we're trying to find the absolute minimum for the x function. So to do that, we need to find critical values and then test those along with the endpoints to see what gives us back the smallest or the most negative value. So for the derivative here, x prime of t, which is what I'll need for critical values, I need to use the product rule. So I've got my factors of e to the negative t and sine of t, and their derivatives, which are negative e to the negative t and cosine of t. Using the ribbon to multiply that out, basically u prime v plus uv prime is my kind of format here. I'm going to have x prime of t equals negative e to the negative t times sine of t, plus e to the negative t cosine of t. And again, I want this to all equal 0 for critical values. So in order to solve this, let me start by factoring out a negative e to the negative t. That'll leave me inside with a sine of t minus cosine of t, and all that equals 0. Now, negative e to the negative t, it's an exponential function. There's no way that's ever going to equal 0. But sine of t minus cosine of t might equal 0 somewhere. To figure out where, this is kind of tricky if you've never done it before. It turns out you have to add cosine to the other side, and then we have to actually divide both sides by cosine. Now, normally this would be kind of illegal, dividing by something with a variable, but it turns out that sine and cosine can't be 0 at the same time, because we're talking about x and y values on the unit circle, and since we're guaranteed that we're on the unit circle, if one of these is 0, the other would have to be 0, and then you'd be talking about the point 0, 0, which is not on the unit circle. So since these can't both be 0 at the same time, and they equal each other, neither one can be 0. So long story short, dividing by cosine of t does not mean dividing by 0. So dividing both sides by that, we have sine of t over cosine of t, which is really tan of t, and we have a 1 on the right side. Inverse tan of 1 is going to be pi over 4 and a bunch of other things as well. Now, we only care about values between 0 and 2 pi, so the only other value here other than 45 degrees that matters is 225 degrees, the kitty corner angle on that. That's going to be 5 pi over 4. So those are our two critical values. Now we're going to plug these along with 0 and 2 pi into this original function. So plugging in 0 to start with here, we've got, let's see, e to the negative 0, that's just 1. Sine of 0 is 0, so this whole thing comes out to 0. That seems like a pretty low value. Let's see if we can do better, though. Next, I'll do pi over 4. That's the next one in line here. So e to the negative pi over 4, nothing special happening there. Sine of pi over 4, that is going to be radical 2 over 2. So this is going to be root 2 over 2 times e to the negative pi over 4, and I have no idea how I'm going to try comparing this to other things, but let's look at the other things first. At the very least, this is a positive number, so that means it's not going to be the absolute min because we already have something that's 0. Let's keep going. 5 pi over 4 plugged into all that stuff. Sine of 5 pi over 4, that's going to be negative root 2 over 2. And then we have that e to the negative 5 pi over 4 term there as well. And finally, we have 2 pi plugged in. So sine of 2 pi is actually 0, so this whole thing gets zeroed out. Comparing these, we have zeros, we have a positive, and we have a negative. Not worrying about the exact decimal values of any of these things, I think it's pretty common knowledge that a negative is going to be less than 0 and less than positive numbers. So that means the negative wins. The negative is our absolute min, and that happens at a time of t equals 5 pi over 4. For the second part of this very rare two-part free response question, we just need to find the value of the constant a for which x of t satisfies this crazy equation. Okay, so this is kind of a weird question, but basically we need to figure out x double prime of t. We already know x prime of t. We already know x of t. So we need x double prime of t. Then we need to plug all of that in this equation, and hopefully the only thing that's going to be left to solve for is going to be a. But we'll have to cross that bridge when we get there. So here's x prime of t, which we found in part A. And now we just need to take the second derivative of that, which is going to require not one, but two product rules, one for each of these terms. So that gives me 2 box and ribbons to set up. So for the first one, we have negative e to the negative t times sine of t. Derivatives there are going to be positive e to the negative t and cosine of t. And for the next one now, this second term, we have e to the negative t and cosine of t, whose derivatives are negative e to the negative t and negative sine of t. Using ribbons to multiply all this out, x double prime is going to be e to the negative t sine of t minus e to the negative t cosine of t. And moving on to this next one, we have minus e to the negative t cosine of t minus e to the negative t sine of t. Yeah, I know, they all look kind of the same. But let's see if we can clean this up a little bit. So we've got, let's see, we have an e to the negative t sine of t term here. We have a negative version of that at the end. So those are actually going to cancel. That's a good thing. We also have two of these negative e to the negative t cosine of t terms. So when the dust settles, this can all be simplified to negative 2 e to the negative t cosine of t. At this point, we've got what x double prime looks like. We're going to have to plug that in along with x prime and x into this a x double prime t plus x prime of t plus x of t equals 0 formula here. So we have a times this x double prime stuff we just came up with, plus x prime, that's this stuff up here that I'm going to put in hot pink. And then we have the original function x also getting thrown in there. That's this e to the negative t sine of t stuff, and I'll put that in blue. And that should all equal 0. So let's see if we can simplify this at all. Well, we have a negative e to the negative t sine of t and a positive version of that over here. So those are going to cancel. That leaves me with negative, so a times negative 2 e to the negative t cosine of t and this other e to the negative t cosine of t term. Now, from these, I notice that there's a lot of common factors here. These both have an e to the negative t. They also actually both have a cosine of t. I am going to factor both of those out, and that's going to leave me with a negative 2a plus 1, all of that equaling 0. Now, the key here, in order to make this thing true, they said that we have to satisfy this equation for all t values between 0 and 2 pi. What that's essentially saying is I'm not allowed to just pick t values that zero this thing out, because I need this to be true for all t values between 0 and 2 pi. So yeah, there are some values I could pick of t, like pi over 2, that would zero out this cosine term, but we need something that's true for more than just pi over 2 and 3 pi over 2. So that means the only way to make this equation true is if this parentheses with the a in it has a value of 0, which means if we set this equal to 0 and solve, so subtract 1 and divide by negative 2, that means a must absolutely have a value of positive 1/2 in order for this equation to come out true for all t values between 0 and 2 pi. So that's our a value, 1/2.